All right, let's talk about some of the information necessary to complete Lab 6. So with this lab, we're looking at different pulley systems, and there are a couple of terms that we need to use that are slightly different than what we had in lecture. So we've talked about mechanical advantage already, and for the most part, when we talked about it in lecture, what we really meant was ideal mechanical advantage. So that's a reference to basically how a system is supposed to work. And in the ideal case, if everything's perfect and everything works the way it's meant to, these are the perfect numbers that would come from different attributes of a system or a setup. So dealing with the dimensions of a ramp or the size of a wheel and an axle or number of ropes and pulleys, things like that. Actual mechanical advantage is a separate term for how systems really work. So, in a real life scenario, typically things don't work out as well as you'd hope. Same thing happens with mechanical systems. Usually, there's a loss of efficiency. So, mechanical advantage, actual mechanical advantage is going to be less than ideal mechanical advantage. There's friction and forces we can't see, and error in measurement and assembly and all kinds of stuff. So typically these numbers are going to be different from each other. In an ideal world, IMA is going to be 100% because it's a theoretical number, and AMA would also be 100% if it worked perfectly. But again, that's not typically what we see. So we're going to draw a couple of pulley systems. I'm not going to do all 6 because I think we can do a few examples, and maybe I'll skip to the last one because it's a little more complex, and then we can go from there. So if we have one fixed pulley, draw a straighter line than that though. If we have one fixed pulley, so say there's some bracket or support here, there's a pulley that comes down, and we have a rope run over it. So it's called fixed because the pulley can't move out of position. It's fixed with some bracket or hook or assembly that attaches it to a ceiling or support. Let's say that we've got some output mass that's here, so something that we're trying to hold up. Then we have some input mass that we can use, basically create force and balance the system. Our ideal mechanical advantage here is going to be 1. What happens is your input mass, which creates the tension or the input force that eventually runs into the system, doesn't normally count towards your mechanical advantage. What happens is we're counting the number of ropes or supports that directly connect to the weight that we're trying to lift. So in this case, you can see one rope comes down. This tension in the line runs over the pulley. It doesn't change the amount of tension, but it changes the direction of it. So you think about it, both of these masses are trying to pull down, so they've got tensions that run through and balance. And because there's only one support that eventually connects to this block, then there's only an advantage of 1. Now, I do want to show you a different sort of example that is not part of this lab, but there are references to it in the textbook, and it's good to see. So that was one fixed pulley. Say we have one movable pulley. So I don't know, let's call this system 0 because it's not part of the lab. So one movable pulley. In this case, what we would have, we'd have some sort of support at the top still. We'd have some pulley that can move its position with the weight that we're trying to pick up. And so in this case, we'd have to have a rope that runs this way and then a rope that runs up. And we wouldn't actually have an input mass this time because there'd have to be a person here lifting up on this. A person apparently with really long arms lifting up on this. And so now the support comes not from another mass, but from the tension that's coming up this way and the tension that gets duplicated up this way. And so we do want to be careful. It is not technically true that all the time the mechanical advantage is equal to the number of pulleys. Officially, it's equal to the number of ropes that give support towards the mass we're trying to move. But we're not typically going to be looking at systems like this. Okay, so that's just sort of a one-off example. I wanted to show you that there are some exceptions and some weird sort of cases and ways that you can set up pulleys, but we're not going to look at that any further. So back to our more standard examples. If we have one fixed and one movable pulley, again, the fixed pulley is going to be attached to some bracket or support. It's not going to be able to move out of position. But a movable pulley does exactly what it sounds like, and it's going to move up and down with whatever load we're trying to lift. So the thing we want to move is always going to be the output, because that's where your force needs to go in order to start making this move. Then we're going to have some rope that runs into the system, runs around both pulleys, and then connects to somewhere. So I've slightly exaggerated the path of the strings just to make it easier to see, but we would have some input mass here. That is not going to directly lift on the load. So this does not count towards mechanical advantage. But if we look at where the load is, there's a rope that comes up this way that gives support, and a rope that comes up this way that gives support. So whatever initial tension is created from the input mass, that tension, that force rolls over the pulley, it changes directions, and then helps to lift the thing down here. But on its own, this thing is not doing the lifting. It just creates the tension that feeds into the rest of the system. So if we look, there are two ropes that run up and down and hold this mass. So our IMA is 2. Then I want to leave as a challenge, try to draw systems 3, 4, and 5, and I'll skip and draw number 6. You should easily be able to find examples in the book or online if you need the help, or you can email me or ask questions. But I think overall the picture is going to be relatively easy to draw. So let's skip to number 6. We've got 3 fixed and 3 movable pulleys. So the fixed ones, again, are going to be fixed or attached to some bracket. So something like this. The 3 movable ones are going to be on a bracket and attached to each other, but then they're also going to be free to move with the load itself. So something like this. And then we have to have some rope that runs through the system and connects all of these, because obviously without a rope, this thing's just going to fall down and they're not interacting with each other. So this is going to run around the first pulley, around the next biggest pulley, then around here, and just sort of wind our way in. Okay, so something like that. The input mass would be out here, and ironically, my poor drawing skills, the input mass is now going to be physically much smaller than the output mass, because this is going to gain help from the fact that the tension is repeated between the different pulleys. So this is not directly adding to the mechanical advantage. It just creates tension. That tension rolls over the pulleys, and then up and down between the pulleys is where that force gets repeated, which helps us gain mechanical advantage. We want to remember that every different rope that helps to support this mass down here is adding towards the advantage. So the ones that are probably obvious, that these that come around here, but remember that all of these pulleys would be on a bracket with each other. So there's also a rope that comes this way, and then another one that runs this way and this way. So if we look, our ideal mechanical advantage is going to be 6. If it's difficult to count those based off of where the pulleys sit, then sometimes you can just kind of draw a line through and see how many times the ropes hit that line in the middle. 1, 2, 3, 4, 5, 6. For our cases, it is going to be the same as the number of pulleys, but again, officially, technically, it's based off of ropes and not pulleys. So there's a few different ways you can run through and get that answer. Okay, so looking at the data that we want to collect, I was very unoriginal in how I named and numbered and asked you to make these systems. So system 1 has an ideal mechanical advantage of 1, and that's a perfect 1. We counted that. We looked at the ropes running up and down, so it can't be like 1.5 or something. It's 1. And then this one is 2 and 3 and 4 and 5 and 6. Technically, we only drew 1 and 2 and number 6 so far. I asked you to do those 3 in the middle, but I think there's an obvious pattern that makes this easy to spot. Our output mass is a thing that we're trying to lift, and the way we're going to build these in class is we're going to have a set of pulleys that has a mass of about 50 grams. From the bottom of that, we're going to hang a hook that's 50 grams. and we're going to put a mass on top of the hook that's 500 grams. So it's not perfect, but it works reasonably well. If we add these up, say we've got 50 grams, and 600 grams. If we put these things on a balance, then we'd have some decimal places, but without doing so, our best estimates are to whole numbers. And so adding these up, everything is whole numbers, so we're going to get an answer that's a whole number, because I accidentally wrote 600 grams. Sorry, I was thinking of the answer already. 500 grams is on the bottom of that, and I accidentally spoiled it, but that's going to make roughly 600 grams total. Okay, so we don't build the first setup because it really can't work any other way. If there's just one rope and one pulley like we had on setup 1, it's going to be necessary. It will have to be that there are 600 grams on the other side to balance as well. So it would take 600 grams to balance 600 grams. We can find the actual mechanical advantage for how this system works by taking and dividing those two numbers. So divide a number that's not 0 by itself, or infinity or something weird, then you get 1. To preserve significant digits, which aren't going to be a huge deal here, but just to talk about them, 3 digits divided by 3 digits means I want an answer with 3 digits. So technically speaking, we'd have 1.00, which, again, still looks like 1. Then my efficiency takes my actual advantage for how the system really works compared to the ideal advantage for how the system is supposed to work, and then compares those by finding a ratio and then multiplying by 100 to scale it up to 1%. So 1 divided by 1 is 1. Then multiplying by 100%, go ahead and say that that's 100%. Now, because these are all using the same masses hanging down, then this is going to be 600 grams all the way down on this part. But what's going to happen is, because of our advantage and using more and more pulley systems, more and more of those ropes share the weight and split this down, is that your input mass is going to get smaller and smaller on the way down. So in theory, we can estimate from our ideal, again, if it works perfectly, that 600 grams supported on 2 ropes means that we need 300 grams to create the initial tension. And so let's say, I'm going to make up a number. Let's say that this one really ends up taking 305 grams. We don't need the bar on this because the 5 on the end will automatically be significant. Then when we go to find the actual mechanical advantage, the 600 grams from the output is supported by the 305 grams from the input, and we get an actual mechanical advantage of something like 1.97. And if we look, well, oh no, that was supposed to be 2. It wasn't quite there. And so if we take 1.97 divided by the 2 for what the ideal number was supposed to be, then multiply by 100 to scale it up, then we get something here like about 98.5%. Okay, then looking at the next one, and we're not going to do all of these. We're almost done with the part we're looking at together. But we've got IMA 3 for setup 3. So in theory, 600 grams should be supported with 3 ropes. So the initial tension should be created by a mass of about 200 grams. Let's say that this time 198 grams to balance. So it takes a little bit less mass than it was technically supposed to. We still run through the same process. It won't change the math part at all. So we're going to have the 600 grams divided by the 198 grams that supported it, and we get something like 3.03. You'll notice that our IMA, our ideal number that should have been perfect 100%, was 3. We actually went very slightly over that. And that's going to happen sometimes. It really shouldn't, but it will anyway, because of friction and misalignment of pulleys and a few other things that we really can't measure. If you could really make something more than 100% efficiency, then you could feed that energy back into the system, run it again, and it would just keep giving you more and more energy. It would be similar to like a credit card, except it helps you instead of taking money away. If any of you can ever create a system that is proven to be more than 100% efficiency, then patent that immediately, add my name on there for the inspiration I have given you, and we will buy matching yachts and race them once a year. Because that would be like limitless free energy. It would be world changing sort of thing. So we don't really trust that. We understand there's probably some issue that we can't see that's causing the pulleys to bind or something to hang in place when it shouldn't. Okay, so 4, 5, and 6 would work the same way, and eventually you want to find the average of these. We hope the average is just somewhere close to 100. In theory, it should be exactly 100, but typically groups are getting numbers a little higher, a little lower, just depending on what it takes to actually balance. All right, then that should pretty much take care of everything for today.